Memory. Forward. Try it again. Okay, now we'll pretend I didn't just do this. Oh, darn. Okay, our speaker this evening is Diana Hannikainen. That's as close as I can come. Elaine will be up to introduce her in a second, but I've got two announcements I wanted to make. Number one, on the 23rd, right? On the 23rd, and I think that's a Monday?
Monday.
That's a Monday evening. On the GAAC website, there's an announcement. You can get all the details. There's a dark sky and your health and your environment talk at the Manship properties. You've got to pre-register and they'll send you information. It's free. It doesn't cost anything, and the link is right there on the website, and I will be sending that out to the listserv as well. Okay. That looks like it's going to be a lot of fun, Bill. And Mario will be speaking there on each other's specialties, which we're all looking forward to. Okay, the other announcement is our first star party of 2025. We're going to try it again. Visions of Lucy and the football.
Exactly.
Right?
Did you pick a clear night this time?
Pardon me?
Did you pick a clear night?
I forgot. I forgot to specify that. No, it's the 28th, I believe.
Yes.
Saturday night, the 28th.
This month.
Say good things, think good thoughts about clear skies. We haven't been out with a telescope since November. Well, we got to have a weekend. We can't have moon and no clouds would be nice. So that's the two things. All right. There's tonight's meeting, which is going to be a lot of fun. There's the get together at the Manship facility, and then there's our first star party. So plan ahead. Saturday night, the 28th, Halibut Point State Park, up by the visitor center. You know where that is. Come see us. If the skies are clear, we're going to set up a bunch of really cool telescopes, and just for you to look through. So have the good graces to come and look through them. Okay, thanks.
Parking is in the parking lot.
Parking is in the parking lot, and I will put this on the listserv as well. So come on up, Elaine.
If you bring the scope and drive it in.
Yeah.
Like as usual. Hi, everybody. Welcome to GAAC.
Yeah.
Tonight's speaker is Diana Hannikainen, and she got her bachelor's degree in Scotland, and then she went to Finland partly to discover her Finnish roots and partly to get a master's and a doctorate in high energy astrophysics. She joined the staff of Sky and Telescope in 2017, and in 2024 became the editor-in-chief. So let's hear it for Diana.
Personally, I am so excited to be here tonight. I have understood this is a very laid-back, relaxed club, a meeting. And so I thought that we would have a very laid-back and relaxed talk this evening.
Good.
So,
Long wavelength.
a very long wavelength. As Elaine mentioned, I went to Finland. So I did my undergraduate degree at the University of Edinburgh in Scotland, and I did it in physics and astronomy. And I knew that I wanted to continue in research at the time. And I went to the University of Helsinki in Finland to pursue my postgraduate studies. While I was there, I also worked a lot at the University of Sydney in Australia. I did some of my PhD studies there and some research there. And my PhD studies were on the multi-wavelength observations of microquasars. And microquasars are small-scale analogs of quasars. And to be able to observe microquasars, I observed you use X-ray satellites because the accretion disk radiates in X-rays, and then the radio jets radiate in the radio. And so I had to use radio telescopes. When I started at Sky and Telescope, a couple of years afterwards, I thought I would like to write an article about radio astronomy. And I thought, okay, I'll write about radio astronomy, about the different emission processes, about the different objects in the universe that emit radio waves. And I thought, okay, I'll write about microquasars, this and that. And then I realized, as I was writing, I went to the origins of radio astronomy, and I realized it's an absolutely fascinating history. I knew nothing about it because, of course, I only used radio telescopes. I analyzed the data, and I had never really investigated how did radio astronomy come about. And so I'm going to share some of the things that I found because I thought it was really exciting. First, we have to figure out how to change slides.
Arrow key,
Yep.
up arrow. Okay, enter key.
Tried that.
Well, of course.
Be all set.
Do we need to?
You have to turn it off and on again.
No, let's not do that.
Okay, something happened.
Okay.
It looks like it might be the trackpad.
Mm,
No,
It's just slow.
okay, it's just slow.
Mm.
We'll get there. So we're going to go down the path a little bit about, how radio astronomy came to be about. I think there's one thing I'd like to share at the beginning is that something that maybe not everybody knows is that there are so many objects out there that emit radio. We think of the classic quasars as radio emitters, but our sun is a radio emitter. Pulsars, of course, rapidly rotating neutron stars are radio emitters. The Milky Way itself is, all the interstellar gas and so on. The planets are radio emitters. And these are the objects that I studied for my research. So microquasars, you have a compact object accreting matter from a normal star. That matter swirls around the compact object in an accretion disk. The accretion disk emits X-rays, and then there are these bipolar jets that shoot out at relativistic speeds, and they radiate in the radio. And of course, we have the quasars, the classic quasars, where you have a supermassive black hole in a galaxy, and the black hole accretes matter from its host galaxy, and also has these relativistic jets shooting out in two opposite directions. So radio waves permeate the universe, and a quick reminder of just where radio waves sit in the electromagnetic spectrum. We know this is the optical, or this is the visible range that we're very familiar with because our eyes have adapted to that wavelength range from the violet to the red. But it actually occupies a very small, a very narrow range in the electromagnetic spectrum that stretches from the short wavelength end or high energy end, the gamma rays. They are the highest energy radiation that we know of. Gamma rays, you go to X-rays to ultraviolet. And then on the longer wavelength side of the visible spectrum, we go into the infrared, microwaves, and finally radio. And when we talk about radio, when we discuss radio astronomy, we talk about radio emission and so on, we often talk about the emission in either wavelengths. So we talk about centimeter radio waves, millimeter waves, well, that would be the sub-millimeter range here, but meter waves, or we talk in frequency, megahertz and gigahertz. But just to bear in mind that the radio waves are at the longest wavelength end of the electromagnetic spectrum. Before about 1930, the universe was very visual. We only learned about the universe through what we could see with our eyes. There was a little bit of dabbling in infrared astronomy in the 1800s, but not a lot came out of it. So most of what we knew about the universe was visual. We had William Herschel with his fabulous contraptions that he constructed to do his phenomenal sweeps of the sky, and he cataloged all his objects and so on. At the time, the only way to record what an observer saw was by sketching. And then slowly in the late 1800s, photography was developed. And so astronomers and researchers were able to record their observations in a more permanent, in a more objective way. Because of course, sketching is can be subjective. And through photography, it was more objective, but it was still all only visual. And the universe was very local. Until the early 1900s, we knew about the nebulae out there, we knew about planets, we knew about stars, we knew about clusters, but nobody really knew where they were in the universe. We didn't know if they were near, if they were far. Our universe was very local still. And then, of course, the amazing observations of Besto-Slipher, and then followed on by Hubble and Humeson's studies on the redshift distance correlations, and then later on in the 1920s with Georges Lemaitre, when they established that the universe was expanding, we started to understand that we were occupying a very small space in a very vast universe, but it was still only visual. All we knew was what we could see with our eyes. And but in the early 1930s, a revolution was about to come forth, and it was started by a young physicist and engineer by the name of Karl Jansky, and he was employed by the Bell Telephone Laboratories. This was the era of nascent radio communications. Radio science was developing. And engineers at lab were annoyed by, let's say intrigued by the sporadic static that they perceived in their radio communications. They wanted to get to the bottom of what this static was. So they asked Jansky to investigate. And to do this, he built a telescope that was just simply out of brass piping and timber. And this is the contraption that he built, and it was about 30 meters across and 6 meters high. And here's the chap, for scale. And he mounted this. He thought, okay, so he's got this thing. It can capture, it can capture some of this. He was going to try and investigate the static and this interference and so on. But then he thought, okay, to really get as much exposure as possible, or to be able to capture as much as possible, he mounted it, this thing on the Model T Ford, so that it would rotate fully every 20 minutes. And inevitably, it got the name of Jansky's merry-go-round. And so that's what he used to investigate this type of interference. And he was able to isolate 3 sources. One of them was local thunderstorms, and he knew that that was not what was the source of annoyance to the Bell engineers. He knew that there were distant thunderstorms, but those too could be isolated in the data and so on. So he knew it wasn't those. But then he noted that there was a steady His type of static of unknown origin. And that's what he set out to probe. And initially, he attributed this His to the sun. He thought, maybe the sun could be the source of this interference. Mm-hmm. But he was clever. And he pointed to his, he waited for, during the solar eclipse of August 31st, 1932, he noticed that interference did not diminish during that thing. So it couldn't have been the sun, because that static was still there. So he proceeded to collect data, and he collected a lot of data, and he plotted that data. And here on the left, we have time on the bottom axis and azimuth direction on the top axis. And you see that there is a regular variability there with a peak about every 20 minutes. And if you recall, his contraption rotated every 20 minutes. And he realized that what he wanted to do with this data was plotted in a different manner. And so he took the data for each day, and he plotted the direction of the arrival against the time of day for each month. He collected all the data for each month, and he noticed that there was a pattern there. And so what he spotted specifically was that the intensity of the waves was independent of the time of day, but directly dependent on the hour angle of the direction of arrival. And he saw that throughout the year, the direction of the arrival changed gradually throughout the nearly 360 degrees during 24 hours. In fact, 23 hours and 56 minutes was exactly the time that this direction changed. And as astronomers, we know that that is, yes, exactly, sidereal day. So this shift At the end, so he noticed that that the direction so it moved during the year, but then at the end of the year, it was back to its initial position. And he could conclude only one thing from that. And this is a quote from his paper, which was, to one familiar with the manner in which the heavenly bodies change their positions hourly and daily, these facts indicate that the direction of arrival is fixed in space. And that was a very important statement, because it was the first time that scientists had detected a radio signal from outside of the terrestrial sphere. And he noticed that the signal was strongest in the direction of the galactic plane, and it was around right ascension 18 hours. And that we know that's somewhere in Sagittarius, and we know that it coincides with the center of the Milky Way. And of course, today, parenthetically, we know that that is the location at the center of our Milky Way. We have our supermassive black hole, Sagittarius A star. This discovery was publicized widely. The New York Times got very excited. And on May 5th, 1933, they had this column. Okay, so they weren't hugely excited because it wasn't big headlines, on the front page. But still, radio waves trace the center of the Milky Way. And there was a lot of excitement about this, and people started talking about it. But yet, what I think is very sad, note the year is 1933, and by 1935, at a conference, there were barely 24 people in the audience to listen to Jansky talk about his results. Of course, we also know that the 1930s was a very difficult time. There was the Great Depression. There were all sorts of things going on. So maybe there was other stuff involved as well. But still, this breakthrough result, 2 years later, nobody was there to listen to him. But what we do today is, in acknowledgement of the work that he has done, we name the unit of flux density the Jansky, and it's abbreviated JY. There were other people who got interested in what Jansky was doing, and one of them was John Krause. I think he was at Ohio State University, I think, and he was absolutely creative in the manners in which he wanted to explore how to try to understand these radio waves a bit better. And one of the things he did was he just mounted a dipole on the top of his Studebaker that was connected to all kinds of detectors in the back seat of the car. And he would make his PhD student drive the car around while he was there monitoring what was coming on in through the detector. And there are all kinds of anecdotes about, they'd drive through towns and the police would stop them and ask them what they were doing. And they had all these, half the time they didn't believe, the police wouldn't believe what the stories that these two were saying. But that was one of the early experiments, and I think it's incredibly creative and delightful. And then there's also another engineer at Bell Labs, Edmund Bruce. And he simply mounted this wire that he just folded up like this. And they were doing early experiments. Not many results came of those because we would have heard of them, but they were trying, and each little step brought something more to the field. But the next breakthrough was Grote Reber. He was an electrical engineer and he was an amateur radio operator. He was one of the few who took Jansky's discovery really seriously, besides John Krause and a smattering of others. And he looked at optical telescopes and he thought, okay, if an optical telescope works, why don't I try that same shape for a radio detector? And he built a 9-meter parabolic dish that he placed in his backyard, as shown in that figure on the right. And amazingly, despite the efforts of John Krause and the one or two other chaps, Grote Reber was only the second person to make, let's say, official radio astronomical measurements in the history of radio astronomy. And I think this is a an indication of the times and what was going on, but he was the only active radio astronomer, because Jansky had kind of given up after the conference in New York. So Grote-Reber was the only active radio astronomer from 1937 until after World War II. At least who has left a legacy behind in terms of papers and results. And one of the amazing things he did with this 9-meter dish in his backyard, he was able to construct a map of the Milky Way. Crude, but he was able to construct a map of the Milky Way. And this is the results. So these are our contour lines that show the intensity. And he noted a concentration of intensity in Cassiopeia. And now we know that that is GAAC. Then the supernova remnant. Then in Cygnus, he spotted a concentration of intensity in Cygnus that today we know is the quasar Cygnus A. And he also found a signal coming from the galactic center, so which we know is Sagittarius A star. So with this simple parabolic dish in his backyard, he came up with some pretty significant results. Of course, they didn't understand what those sources were at the time. We only learned about the nature of these sources later on with more sophisticated instruments and detectors. But those were the first glimmerings. And so then, of course, we have World War II that comes along, and science and a whole bunch of other things, you know, life, the normal course of affairs ceases and everything's in turmoil. But there's one thing that progresses, and that is radar technology. And the Brits were very the Brits were very much into radar technology development, the Americans and the Australians. And the Australians is important for what's about to come. After World War II, there were all these radars that were lying around unused. And a couple of intrepid scientists at the CSIRO in Australia, CSIRO is it's akin to the NSF here in the United States. Forgotten what the acronym stands for, I really should remember. It's research organization for sure. And a couple of people thought that, okay, so we have these unused radars, what can we do with them? And there was one radar that was atop a cliff north of Sydney, and they thought, okay, we'll use the radar as we'll point it towards the sort of vaguely towards the sun. And on calm days, when the sea acted as a mirror, what they were able to do was they were able to capture a direct ray from the sun and the reflected ray off the surface of the sea. So effectively, they had what we call a baseline of 100 meters. And with this, have I switched language?
I haven't switched language. Turn to Italian.
So with this incredibly ingenious setup, very simple but ingenious setup, they were able to map sunspots. So these are observations taken separated by about a couple of months, but they were able to actually map the location of sunspots on the surface of the sun.
They got that detailed with that primitive equipment.
They did,
I'm impressed.
yes. You can read about it in the 1947 Proceedings of the Royal Society of London. So the Australians were real pioneers in the development of radio telescope, radio detector technology, and the Dutch were as well, the Brits were as well, and of course here in the US, but the Australians really took it to heart. And in the early 1950s, Bernie Mills, who's based in Sydney, what he did was he set up two arms that ran north-south and east-west, just a wire mesh. dipoles and so on, and that operated for quite a few years until they decided to upgrade it, and by upgrading it in the late 1960s, they removed one of the arms and they renamed it the Malungal Observatory Synthesis Telescope. It's about 800 meters long, and it's just a cylindrical paraboloid. It's outside of Canberra. And this is one of the instruments that I used during my thesis work. I had data from it and I absolutely love it. It's just a simple cylindrical paraboloid. It's a synthesis telescope in the sense that you can't really direct it in any, you can't really say, oh, my target's over there, so I'm going to direct the telescope there, or my target's there. What you have to do is wait for the sky to pass overhead and you collect what you get. But it was still a fantastic instrument. It's still operational today. And in fact, they have refurbished it and they're doing a lot of new research on fast radio bursts and so on. So it's an instrument that essentially started in 1954 and is still going strong, albeit in a different configuration. And the Aussies are very resourceful. They decided not to use lawn mowers, so they just release, the sheet onto the lawn, and that's how they keep their lawn neat. And then there was another chap, Dr. Christensen, also at the University of Sydney, and he set up this in the late 50s, this amazing series of these weird looking antennae here. But one of the things about Australia, so as I mentioned, I did some of my PhD work in conjunction with the University of Sydney. And it was through a series of coincidences that I got to meet a professor at the University of Sydney while I was studying. I'd gone to Finland, and I just want to show, I did not grow up in Finland. And I spent years in places like Brazil and so on. There's not a lot of snow there. And so I was quite shocked to find, myself one day, that's snow. That's my office window. I was not on the third floor. I was on the first floor, so this is not a huge amount, but it's a bit, and it was also there was a bit of drift as well. But it's a bit startling to walk into your office and find that there to greet you. But so I developed this relationship, student, professor, and then later on working relationship with my lovely mentor, Professor Richard Hunstead. And Richard Hunstead was a lecturer and researcher at the University of Sydney. And as you know, Sydney is in the Southern Hemisphere. And in the Southern Hemisphere, the academic year runs from March to December. And so whenever I would ask him, when can I come to visit him so that we can do some work together, sometimes during my studies, sometimes, later on, he would always say, well, March to December isn't such a good time because I'm teaching and so on. Why don't you come in January? Well, what do you think I did? Of course I went, because this is the view that greeted me. It'll come there. That's the view that greeted me when I would arrive, 2 days later, and it took so long to get to Australia. So of course I took every single advantage to be down in Australia, meeting Richard and so on. But I just want to do a little anecdote besides radio telescopes. How many of you have been to Australia? Yeah, quite a few. So what's Australia known for?
Kangaroos.
Kangaroos, for sure.
Chlamydia.
Koalas.
Isn't it scary spiders?
What came from online? Scary spiders. Yes, what came from online?
Koalas.
Koalas as well. But yes, what you're all saying is wildlife. And Australia has phenomenal wildlife. And this is my beloved mentor who's no longer with us, but this is where I would spend my mornings after, coming from Finland with all that snow. This is where we'd have lunch and dinner and breakfast and so on. And this is my darling mentor with the rainbow lorikeets that are absolutely adorable. Cockatoos. Cockatoos are phenomenal. They are such clowns. And this is the little possum that would come and visit us at night. She loved apples. She absolutely loved apples. I give her apples. But then we also had blue bottles. I think you know them here as Portuguese men o' war.
Oh.
And they would hang out in clusters like that. We'd also have a blue-ringed octopus. I don't know if you know of the blue-ringed octopus. Here's a tentacle. So we were playing around in rock pools. So one of the things, the beach outside of Sydney, north of Sydney, it's very cliffy. And there are places you can go. There are lots of rock pools. And rock pools are fantastic because you find all kinds of treasures in there, really, fun shells and fun rocks and so on. And we were literally like 2 seconds before this, we all had our hands in this water, we were picking up fun things. And then the tentacle of this blue-ringed octopus came out and it startled us, I must say. And then, of course, spiders. This is the sort of bella that I would find regularly, outside my, that's the shower, as you can see, the shower room.
Looks too big for a newspaper.
You just leave them alone. Plus, when you spot, all the, Australia is lovely. So along the way, so now we're in the 1950s and we're doing some serious developments in radio, telescope construction, dish construction, and detector construction. And I'm just going to run through some of the big discoveries of the 60s and 70s. And of course, one of the phenomenal discoveries was the microwave background in 1964 of Arnold Gonzalez and Robert Wilson with the Holmdel horn antenna, which, by the way, I don't know if you read the story, about a year ago or so, it was in danger. The antenna, they were, wherever it is there in New Jersey, right? They were going to just take it away and scrap it. But a couple of people, I think especially from the Westchester Astronomy Club, Larry Faults and so on, they went and they saved it. So now that can stay where it is, where it made the discoveries, but it was in real danger of disappearing forever. And this is a big historical moment in our scientific history. So very grateful for that. But we know that these two fellows, they got the Nobel Prize for this, and they discovered this. They too were annoyed and sent out to investigate. A hiss that they couldn't quite pinpoint. And after eliminating a whole bunch of things, including pigeon doo, there was a pigeon doo on the antenna, they concluded that the only thing that this hiss could be is the echo of the Big Bang at 300,000 years after radiation decoupled from matter. So that was one of the big discoveries. That was 1964. And then, of course, we have Jocelyn Bell, as she was known at the time, today, Jocelyn Bell Burnell. In 1967, she discovered pulsars. She was a graduate student at the time in Cambridge. And she, her supervisor, Anthony Hewish, had told her that, okay, she had to go do this, do that, and so on. And she discovered this very regular signal in data. She said, I think we have something here. And her supervisor essentially dismissed it and said, no, it's not possible. It must be an error in this, an error in that, whatever it is. But she persevered and she said, no, I do believe this is a real thing. And initially they weren't sure, while she was still trying to figure it out. She called it LGM1. Does anybody know what LGM stands for?
Little green man?
Yes. So it was initially called that, and now it has a more official name of PSR for pulsar B1919 plus 21. And in the end, I think we all know the story. Anthony Hewish, her supervisor, Martin Ryle, who was the huge astronomer at the time and he was a pioneer in radio astronomy there at Cambridge. They got the Nobel in 74. She didn't, but she was never bitter about it. But nevertheless, so pulsars, as we know, rapidly rotating neutron stars, and they emit a signal every time the jet of particles is pointed at Earth. And then in 1975, so quasars were first identified in 1963 when Martin Schmidt and Bev Oak and a few other people, Cyril Hazard and so on, were able to get a spectrum of 3C273 and placed it at a distance of something like 2.5 billion light years away. Until then, nobody was really sure what these quasars were. But it was not until the mid-70s that the first observations, this is a radio map, and so it shows again the distribution of the emission. And it was in 1975 that the first quasar jet was identified. And of course, after that, quasar science, quasar astronomy absolutely exploded. And today we know of about 1 million quasars out there. Not all of them have radio jets, but in terms of quasars, there are about 1 million such objects. And this is where one sees the power of observing the universe at different wavelengths. So when you look at the universe only visually, like what we knew about the universe in before the 1930s, before we really knew about other wavelengths, we would see the universe only, what our eyes would tell us. And so this is a field with a fuzzy dot here in the middle. And so you look at that and you see, okay, it's a fuzzy dot. Fuzzy dot's probably a galaxy, and okay, what do we do with it? But when you point your radio telescope at it, you know that that fuzzy dot actually has these radio jets. So this is to scale. I plotted this on top to scale. So that's the center of the galaxy, and these jets extend for about 500 million years or something like that. Light years, same years. And this shows the importance of looking at the universe and observing the universe at other wavelengths than visual, because it tells us a lot more about the nature of the source of the underlying physical processes. And then, of course, we have microquasars, which was my topic. And as I mentioned before, we have compact object accreting matter from a companion star. And so the first quasar jet was detected in 1975. And of course, I've hidden the year here, but it's 1979. The first microquasar jet was suspected in 1979, and that's a source known as SS433. And you have a supernova remnant here. And in the supernova remnant, there's a neutron star, and it has its companion, it's accreting matter from the companion, and then ejecting these jets that these are radio maps. This is what we see in the radio. We see the central source, and this is the ejected matter that goes off in both directions. And so those are just some of the discoveries from the 60s and 70s. Of course, since then we have made many more, and I might come to some of them at some point. But so I mentioned that it's important to observe the universe at multiple wavelengths, and that is because each of the wavelengths deliver a certain information about the underlying physical processes that power sources. And so ideally, we would like to observe sources across the electromagnetic spectrum. And as I mentioned, X-ray microquasars, for example, the accretion disk radiates X-rays. So we want to be able to observe these accretion disks. To do that, though, we have to lob satellites above the Earth's atmosphere, because X-rays, gamma rays, these high energy rays don't penetrate through our atmosphere. So to be able to observe X-rays and so on, we need to go above the atmosphere. We know that optical light visible light does reach the Earth's surface to a certain extent, but to be able to mitigate the effects of the atmosphere, we want to put telescopes up high, as high up above the atmosphere as possible. So we look for high mountains and so on. So these all present challenges because it's not simple to build a detector that can withstand the harshness of space and then put it on top of a rocket and get it into the right orbit and so on. It's not easy to bring stuff to the top of a mountain and so on. So one of the advantages of radio astronomy is that radio waves, apart from the longest wavelength radio waves actually reach Earth's surface. And so that means we don't have to do anything more complicated except to build them. But of course, they do pose their own challenges. And the main challenge is what we look for as scientists, as astronomers, of course, is resolution. We want to be able to see things in as much detail as possible. And resolution is, in a simplified formula, the resolution is simply the wavelength divided by the diameter of your detector. So quite simply, the longer your wavelength, the larger the diameter of your detector has to be, so as to make this theta as small as possible. We want theta to be small, because that is what tells you the level of detail that you can detect in your data. So that means if we are looking at the longest wavelength end of the spectrum, what we need is very large Ds. So we have done that. We have built Arecibo, which was had a diameter of 305 meters. And currently there's a 500-meter aperture spherical telescope in China. And these are huge structures, and they are built in natural depressions in the earth. But of course, one of the let's say negative aspects of them is they have little maneuverability. Again, they're like the synthesis telescopes. You just have to wait for your target to pass overhead to get any usable data. There was a little bit of maneuverability in the secondary. You could shift it around a little bit, but that didn't give you, you know, the whole sky by any means. But of course, as we all know, Arecibo is no longer with us because it was following a hurricane, I believe, that the whole secondary and the receivers and so on up there just collapsed onto the dish, and it cracked, and they're not going to rebuild it. So the next step is we can reduce that diameter. We can't have something that's about 300 or 500 meters across. We can go down to, let's say, 100 meters across, and then we can make it a fully steerable dish. But so there on the left we have the Green Bank, and on the right we have Parkes, which is down in Australia as well, and Green Bank in West Virginia, Parkes in Australia. And so the Green Bank is, and these are examples of fully steerable. So you can move them around to wherever you need to in the sky, within limits, of course. You can't put them, you know, vertical or anything. But this too has challenges, of course, and the challenges present themselves in the form of physics, gravity. Gravity is a problem. We also have weather, high winds, and on the left-hand side, you see a photo of the lovely Green Bank telescope on November 14th, and the next day it just collapsed into a sorry heap. It was just too much. The structure just couldn't withstand. It wasn't built properly enough to withstand the effects of gravity over a long time, and the high winds and so on sort of made it a bit unstable. But the good news is that they rebuilt it, and it's currently called the Robert Seaberg Green Bank Radio Telescope. Has anybody been there? I think they do a star party there. I think it's a pretty nice star party. So how do we? Okay, so we can put something that's 300 meters across, 500 meters across in a natural depression in the earth. We can do fully steerable 100 meters. They haven't really been able to construct anything engineeringly sound that's more than about 100 meters across. So how can we obtain larger diameters to better capture these long wavelengths? How can we do that?
The moon's about as far away as Australia, right?
Sorry, what?
The moon is about as far away as Australia.
Just about. So what we can do is we link multiple dishes together in a technique that we call interferometry. And of course, this is what most of you know, the Very Large Array. Today called the Karl Jansky in honor of our intrepid Bell engineer. And it has 27 dishes that are of diameter 25 meters, and they can be moved into 4 main configurations that are imaginatively called A, B, C, and D. And they range from the most compact, which is only about 0.6 miles across, when you have all 27 dishes within an area of 0.6 miles, out to 22 miles. And they operate so that they keep the configuration, because it's not easy to move these things. They put them on these rails and they move back and forth. And so when you apply for observing time at the VLA, you have to specify what configuration you need, and you can only get observations of when the VLA is in that specific configuration. And yeah, so here's just some photos showing, you know, how they have to. That's why they can't just shift it, you know, from day to day. It is a big operation to change the configuration. They're absolutely marvelous dishes. And so we might ask, why go to all that effort? Well, we're going to take a look at a quasar, Hercules A. And we are going to step through the 4 configurations. D, the most compact, when it's 0.6 miles across for 1 kilometer. And we're going to step through each of these configurations and see what data we get. What's the result that we get? So when it's at its most compact, so the baseline is only about 0.6 miles, we are effectively seeing a wider view. And we are seeing the outlines, fuzzy outlines of the lobes of the radio jets. As we go up in diameter, not up in slides, up in diameter. We go to the next configuration, which is the C, which is at 3 kilometers across. We start to see a little bit more detail. You see the central nucleus start to show. And as we go to the next, which is the B configuration, which is 11 kilometers, you start to see even more. You really see the collimation of the jets here, right at the base of the where the ejection starts. And when we go to the highest configuration, we really start to see fine detail. And what is wonderful is when you put all of these together, you get a full picture of what the galaxy looks like. And so here you have the widest configuration, or the most compact configuration gives you the widest view, so you get all the information of the outer lobes. And as you go to the smaller, I'm getting confused here. So yes, when you go to the larger diameters or configurations, then you start to probe the finer detail here in the interior of the target, or towards the closer to the galaxy. And so I think this is a marvelous example of the power of looking at something in different ways. And of course, there's the galaxy, the host galaxy itself is there in the optical. So interferometry itself, is a wonderful technique, but it's really, really complicated. Because what we need to do is these waves arrive from space and they hit detectors. They hit detectors at different times. As they come from the celestial target and they come through the atmosphere, they hit the detectors at different times. So to be able to fully analyze and understand what the physical processes are at the source, we need to make sure that we reconstruct that signal as if it were coherent from the source itself. And so what radio engineers do is they use correlators to I'm looking forward to reconstruct the signal properly. And when you have only 2 dishes, it's one thing. But when you start to have the 66 dishes, for example, of the Atacama submillimeter array in the Chile desert, this is what the correlator looks like. This is the number and jumble of cables that's needed to be able to reconstruct that signal so that it truly represents what the source emitted. And so you can ask, okay, so you have something like an array that is there, the VLA that can go up to 36 kilometers, whatever it is. So you say, why stop at one country? And in fact, we don't. And radio astronomers have developed a method that's called very long baseline interferometry, or VLBI. And the United States has such a system that's called the very long baseline array, or the VLBA. And there are 10-25 meter dishes that are distributed from St. Croix in the Virgin Islands out to Hawaii via a couple of spots here in the US. And that's up here in Massachusetts, that's Haystack, right? Yeah. And the Europeans have their own network, the European VLBI network. And this is where I used to, I worked at, that dot there is one of my former institutes. And then there's the East Asian VLBI network. And so effectively, now you have a baseline that goes, from Hawaii to Virgin Islands. The Europeans NAB, the South Africans, asked them to cooperate, so essentially there's also a north-south baseline that covers the whole globe. And you probably remember the big results that came out in 2019 and then 2022 of the Event Horizon Telescope collaboration when they imaged M87 and then later on Sagittarius Star. And so what they did was instead of just having a set network like the VLBA in the US or the VLBI in Europe, what they did was they borrowed antennas from around the world and combined them. And so this is just a little cartoon of how as the baselines come in, as the image gets constructed. And the more telescopes the more baselines that we can add and connect, the more the image grows. And so the Event Horizon Telescope is probably the last of the biggest results, or let's say concrete projects that we've had, but there are several projects in the making. And one of them is the Square Kilometer Array, and that is collaboration. It started off as a collaboration between Australia and South Africa, but now there are several other countries that are involved in this. And the idea is to build two massive arrays, each one of different types of telescopes. So in Australia, they are using one type of telescope, and in South Africa, they're using an array of dishes. And then eventually they're going to use these two arrays in concert and use them as one big instrument. And the VLA is under, I don't know if they started already, but they are starting an update of the Very Large Array, and they are going to increase from 27 dishes up to 244 dishes. But these new dishes are a bit smaller. They're only 18 meters across instead of 25 meters. But baseline is going to be about 200 times longer than it is now. So that's going to be an exciting project to keep our eyes on. And then there was also space VLBI. The Japanese lobbed a radio antenna into space, and it was a project that was initially called, you don't remember what the V stood for. Oh, VLBI, there it is, right under my eyes. VLBI Space Observatory Program. So if there are any cognac drinkers among you, you will probably recognize the thingy there. But they called it Halka in the end. And the Russians had a program that was called Spectre R, that was completed a couple of years ago, but I'm not so sure. I don't really recall any groundbreaking results from either of these two programs. They were getting some data, but at least it was a first step into experimenting with having an antenna up in space. And one program that, well, who knows nowadays, but until a short while ago, NASA wanted to deploy a wire mesh on the far side of the moon. And they're looking for a suitable crater that's about 1 kilometer in diameter. And the benefits would be manifold. One of them would be, first of all, most excitingly, it would be able to access these longest radio wavelengths that are ionosphere blocks. And it would be a wholly new window that would open up for us in terms of observing. And the other benefit is that on the far side of the moon, there is absolutely zero noise from Earth. And so I hope to see this program go forward. The last I heard, they were still considering it, but this was a couple of months ago. So who knows? So that was the end of, let's say, where we go now. I'm wondering if any of you knows, if you are interested. Okay, so now we've had a lot of smoke in here. We've not had very good weather. We've been talking about that over dinner and other places. But you know what? You can do radio astronomy in your backyard. There is a burgeoning amateur radio astronomy community. If you're interested, it's called the Society of Amateur Radio Astronomers. You can purchase your own little backyard dish, or you can learn how to repurpose your cable satellite dish. Some people have done, and then you're not bothered by smoke and clouds and other things. But so if anybody's interested, they're a very active group, the Sarah group. They do conferences. I think they're annual conferences, and I think you could check them out if that's something that might interest you. And so it's not only astronomers who love radio telescopes. They've also caught the eye of Hollywood. So of course the VLA featured in Contact. That was an amazing movie. Arecibo featured in Goldeneye. And The Dish. Who has seen The Dish? That is an absolutely delightful movie if you get the chance to see it. So that's Parkes Radio Telescope. And it is the story of Apollo 11 and how when, of course, there were tracking stations, you know, after the astronauts left. And as they were orbiting the Earth, of course, NASA needed to keep in touch with them. And there were several tracking stations here, you know, across the eastern seaboard, and then it went across the Atlantic, and there were tracking stations, I think, in Spain, Morocco, maybe, something. Ooh, what was that? And then when they got to Australia, there were a couple on there was one on the west coast, I think, and then over there in Parkes and Tidbinbilla, which is outside of Canberra. And so this movie is all about what went on during the Apollo 11 mission, at the start of the Apollo 11 mission, and how they came together, they did the tracking there from Australia. It's absolutely delightful. I do hope you get a chance to see that. And I think that is all I have to say. If you are not already a subscriber to Sky of Telescope, we talk about lots of fun things like radio astronomy and black holes and so on. Point your phone at that QR code and you can get a discounted subscription. Okay, thank you so much.
Woo!
I'm going to jump in with the first question, if that's
Yes.
okay, as a matter of privilege.
Okay.
In all seriousness, do they need sheep to mow the lawn because of spark plugs?
That is a very good question, and I do not know.
Oh,
I think they're just being parsimonious.
oh.
Yes, but that is a good question. I certainly think
The West Virginia Observatory, radio, sound.
Yeah, exactly. So certainly back in the day with the older mobile phones, we had to switch all cell phones off whenever we got within quite a large radius of any of these radio telescopes. As soon as you went into the grounds, they'd say you'd have to switch off your mobile phones. And the Molonglo, when I was at Molonglo, so this was the late 90s, and the first mobile phones started to become a little bit more prevalent. And
I'm
one
gonna
of the
stop your share so I can see the online people, if that's okay.
Yeah,
I got
yes,
it.
yes.
I got it.
You got it? Okay. And they showed me, you know, there was a plot of data, you know, like the synthesis map, and through that data there was just a great big, you know, bit of interference, and it was just somebody driving in a car with their mobile phone on. And it took a while before radio astronomer engineers realized that no, we've got to keep our mobile phones off. And nowadays I've understood that in some places they're able to use some kind of filtering system to filter out, but I didn't understand that. But yeah, in West Virginia, that's a radio quiet zone completely. And there was a story from the Australia Telescope Compact Array, which is 6 dishes outside of Narrabri in New South Wales. It nearly made it to a published journal. Somebody was sitting there in the control room. They kept getting, you know, they had the dishes observing something or the other, and they kept getting a signal. And it was very regular. It was every day around noon or so. And so they were like, oh, this is curious. We're getting a real, sort of little outburst every day. So, and it lasted for maybe a week. And then the scientist was quite intrigued by it, and they thought, okay, but then it lasted for a month and 2 months and three, and they thought, no, because it can't be coming from the same place, 2 months late, 3 months late, because we have and they realized it was the microwave in the kitchen. Somebody was, so they had to remove the microwave then. So these are all the things that happened in the early days of gadgets coming into radio astronomy, the sphere of radio astronomy. So
Let's go online. Irene had the first hand up.
Oh, thank you. Diana, this is your avid fan down in Florida. It's great. It's great to see you there. Maybe you just answered the question, but I just wanted you to comment on that 1977 signal that became known as WOW. And was that ever determined to be some kind of interference, or did they ever come to a conclusion about that? You know what I'm talking about, right?
I do, and I just read something about it like a month ago, but I have gone completely blank. Does anybody here remember?
I probably did too and forgot it.
I'm so sorry, Irene. I know I just read. I read about it.
I don't know if they ever came to a conclusion about it, but it was.
They did. I think they did.
Okay, great.
I think, but you know what? I don't remember. You know what, Irene? I'm gonna look it up and I'll let you know.
Oh, thanks, honey. I can look it up.
Because I know I read it somewhere recently. I'm so sorry.
Oh, that's so funny. Thank you. You have enough on your mind. It's a wonderful presentation. Thank you.
Thanks, Irene.
Alan,
Thanks. Great presentation. I've heard you before on Facebook and YouTube. Thank you. Two quick questions. How did we get from all those wiry antenna contraptions to, I think, Jansky's parabolic dish? It seemed like just a sudden jump. And then what is the actual practical difference between, I mean, other than structural, between what you can pick up with like the giant Australian cross versus the very large array of dishes?
Yeah, good questions. So your first question was, how did we get from the sort of wire contraptions and so on to the parabolic dish? That was purely Grote Reber's idea. He looked at the way optical mirrors worked, and he thought, okay, if you have an optical mirror of about I don't know, meter and a half, 2 meters, why don't I make one of 9 meters to see if I can capture radio waves of the specific wavelength that would be reflected by that sort of size. So I think it was simply him. It was he who revolutionized it all just by deciding, okay, I'm going to try this. And your second question about what is the difference with what you let's see. Not being a radio engineer myself, I think it has to do, a lot of it has to do simply with structural issues. Something like a wire mesh like the Molonglo Observatory Synthesis Telescope is very easy to construct. It's very easy to maintain. It's low maintenance. And whereas a dish requires a lot more engineering, a lot more maintenance, and a lot more care. For example, I think the Chime radio telescope up in Canada, okay, no, let me not go there. Let me go back. So when I was working in Finland, and when I pointed out that dot, that was one of the nodes of the European VLBI network, that radio telescope, so it was a 15-meter radio, that's inside a radome. We have to have a radome over that because of the snow and the ice that we get in the air in Finland. So when you have something like a parabolic dish, you need to, it requires a lot more care and a lot more maintenance. And
sorry.
Go ahead.
But you're picking up all the same stuff. It's not one is better at one thing and the other is better at another.
Aren't you using different wavelengths?
Different wavelengths. I was just going to get there. There are.
In the 30s, radios were pretty. 30 megahertz, 100 megahertz was a really fancy radio. It was like hard to
Yeah.
get vacuum tubes to do that.
Yeah,
And the big difference, you mentioned this briefly, but didn't connect that, radar. The radar development in World War II developed all the microwave technology.
Right.
Which not only used those dishes, but enabled you to have circuits that could actually work at those frequencies.
Yeah.
right.
So people moved up to shorter wavelengths.
So,
Oh, sorry again.
no, go ahead, go ahead.
I'm conscious that there are probably other questions. The other thing just struck me as kind of odd when the original guys thought that the radio waves would stop, or the hiss would stop during the eclipse. And that just seemed kind of odd. Don't radio waves go around and through? And why would they have expected radio waves to stop during the eclipse?
It would have been like from a point source. I think he was expecting it, it would be a very focused signal, like from a point source. He was thinking of the sun as a point source, and so it would be a very focused signal. And so then when the moon would have come in the way, it would have blocked the radio.
So the moon will block the radio. Okay.
That's what he was expecting.
Yeah. All right. Thank you. Great talk.
Okay, any other questions online? No. Okay, what about in the room? Yes.
I was wondering how different the math is when you use the different frequencies. You go from the lower to the higher frequencies. How different do those contour lines look?
I think the difference is more in the okay, let me think about this. When you go for one is probing, okay, the different frequencies come from different physical processes, I think, or from different phases of the same physical process. So it depends on where that process is occurring. So if you have a higher frequency, it's just higher frequencies trace certain physical processes and lower frequencies trace other physical processes. So it just depends on how the source is behaving at those frequencies.
So would it be the difference of like light versus radio? How we see light in certain ways, and we see, like with the example of pulsars, you see two very different things. You see the jets, the other you see just
Yes,
a ball.
or like the image I showed of the quasar.
Yeah.
The image I showed of the quasar Hercules A. So with optical, which is very high frequency compared to radio, we see the host galaxy. So we're seeing the stars, the output of the stars, and so on. And with the radio, we see the jets.
Yeah.
So we can't see, the galaxy doesn't emit, the radio jets don't emit. Well, these particular jets didn't emit optical. So that's a very good analogy. So thank you. Yes, that's exactly. We're seeing the different processes.
Any other questions?
I may have a second.
Presentation.
Go ahead.
So we just talked about the sun and how, during the eclipse, it didn't, the radio waves didn't change that. So the sun, despite all the visible light coming to us, isn't a big source, it's not a big source of radio waves.
Okay, so what happened was Jansky was he thought that the sun was the source of this hiss, and so he was expecting during the eclipse that the radio that the hiss would go away, die out, and it didn't. The sun is a radio emitter, and we do see it in the radio, but it's not enough to, the hiss was the hiss was much stronger than what we get from the sun. So even if the sun was eclipsed, it didn't cause a big enough dent in his detection.
Any other questions? All right, well, thank you again.
Thank you very much.
Thank you.
Thank
This was a
you.
wonderful presentation.
Thanks for the magazine.
Oh, good night.
Right.
Thanks, Michael.
Okay.
Good night. Have a good week. Thanks, Mike.
Oh, there's that.